All right, we'll get started. Can everybody at the back hear me okay?
Yes.
Yep, excellent. Look, thanks for coming along and giving up what appears to be quite a sunny Saturday to learn a little bit more about what we've got to offer here in the Faculty of Engineering. You have very wisely come along to the talk about electrical and electronic engineering. I am unashamedly pro electrical engineering, and during the course of the next few minutes I want to explain to you hopefully some of the reasons why I really like it, why I've made a career of it, and give you some idea of not only what it is electrical engineering is about, the sorts of things we're interested in, but what you might do if you were to come here and study. I've rather bravely subtitled it Electrical Forces Rule the World. Not everybody agrees with me, but I'm sure you will after we get started. So, my name is Mark Andrews. I'm a senior lecturer in the Department of Electrical, Computer and Software Engineering. I thought when I started here as a student that I'd be in and out, but I found the whole education process so fascinating and so rewarding that I've decided to, what appears to be, spend my entire life here. That's okay. Now, let's get started. If you know anything about physics, you know that there are 4 fundamental forces in nature. A couple of those we are familiar with on a daily basis. Gravitation, right? We're all sitting in our seats, we're not floating around the room. We're very aware of the effect of gravity. Electromagnetism is another one. We basically know about electromagnetism, don't we? Electromagnetism's got something to do with how radios transmit, and maybe it's got something to do with how light manages to fill this room, that sort of thing. There's also 2 other forces, the strong nuclear force and the weak nuclear force. We don't have anything to do with those on a daily basis, or at least we don't perceive it. They're there, but we don't really notice. So there's really only 2 forces that we really have anything to do with, that we can actually perceive. You're probably thinking, well, wait a minute, what about mechanical forces? Well, it's true, right? This desk appears to be solid. I can't put my hand through this table. It's got nothing to do with mechanical forces. It's all to do with electrical forces between electrons. So in that sense, electrical forces really do rule the world. Okay? There are all mechanical forces, for example, derive their effect from electrical forces. Of the 8 equations that describe classical physics, fully half of them are about electrical things. Right? So this is backing up my claim that that electrical engineering is something that's worth studying, since it describes so much of what we manage to see each day. Now, before we kick off, I just wanted to talk about this guy who had a lot to do with the early field of electrical engineering. He was actually a physicist, James Clerk Maxwell, very smart guy, very mathematically clever. He was able to take all that was known about electrical phenomena at the time, which was things like, if you've done physics at high school, probably things like Ampere's law, electrostatics, a little bit of magnetics, all of those ideas which at the time seemed to be separate, and he was able to pull them all together into one cohesive theory. Now, I'm going to show you what that theory is. Now, if you talk to anybody who specializes in public talks, they will say to you, whatever you do, don't put up any equations. That will just kill the talk. People will lapse into a coma. You'll never get them back again. But of course, I'm talking to people who want to be electrical engineers, perhaps. So I'm going to commit that cardinal sin, and I'm going to put up what are known to us as Maxwell's equations. They're extremely fundamental. And believe it or not, there's very few of them. Here they are. Aren't they beautiful? Now, okay, they don't appear to roll off the tongue like E equals mc squared. And we're not even sure what they mean, and I'm not about to tell you. But I can reveal that things like B, that's sort of connected with magnetism, and that E is a little bit connected with voltages. But you know what? These four equations have been true for at least the last 13 billion years, since the Big Bang. Inside these four equations are hidden probably the greatest technological advances the world has ever seen. These four equations describe everything from how electromagnetic waves propagate through the atmosphere, how light reaches a telescope from a distant star, how it is that electricity is able to be generated in the South Island in a hydroelectric power station and yet somehow appear in your bedroom at home in a socket. These equations also describe how your microwave oven heats your porridge in the morning. These equations are truly amazing. And they are very simple, right? They fit on just a slip of paper. And yet such technological advances really are hidden in there. These equations are still giving up their secrets today. Right? When Apple is able, those of you who are probably just mum and dad here, mum and dad remember the cell phones where you had to pull out the aerial, right? Well, we knew that that was somehow to do with reception and sending radio waves. Where are those aerials now? Well, we don't seem to have them. We still need them, but they're built into the body of the phone, right? They're still in here somewhere. My signal seems to still get out to the roadside where it's picked up by another antenna, and then, I get to talk to, grandma overseas. It's because we used Maxwell's equations to figure out how to make those antennas smaller, funny shapes, still fit in the phone and yet still work. All right? Pretty much everything we study in electrical engineering is built on top of these equations. Okay? That's one of the great, powerful features of electrical engineering, is that there's a truly rigorous foundation to it, right? Embedded deep in physics. So without James Clerk Maxwell's equations, we wouldn't have cell phones. Simple as that. We wouldn't have CubeSats, tiny little CubeSats that we send into orbit for almost no money these days. We would never be able to communicate with them, get data back from these things. We'd never be able to build those circuit boards in the first place without Maxwell's equations. I've already mentioned the microwave. Even the humble electric toothbrush would not be possible without Mr. Maxwell's equations. And while these are fairly simple examples, if you name any advanced application of electrical engineering today, relies utterly on Maxwell's equations. In fact, even more relies on things like quantum mechanics, if you've heard of that. So what have these equations led to? Well, I tried to put all of electrical engineering onto one slide, at least in terms of some titles. And that's quite a bit of stuff, right? 100 years ago, most of these topics never existed, but here they are. Now, it's all right, you don't have to worry, you don't have to study all of this when you come here. In fact, there isn't a single engineering school in the world who teaches everything. Each engineering school teaches just a subset of engineering. There's just too much of it. Now, here at Auckland, we teach roughly the bits that are shown in bold here. Obviously, we don't do things like, nuclear and plasma science, for example, and a few other things. You've got to go somewhere else if you want to do that. But look, it doesn't matter. Because one of the key things about being a student at university is, and this sounds kind of trite, but you learn how to learn. One of the key features of technology is that it's changing all the time. So the things that I learned as a student back in the early 80s, right, that took up the entire degree, now that's only a tiny part of the degree because the technology has moved on so much. And it's not really about, the technology. It's about being able to use critical thinking, your natural talents, your raw intelligence, the skills that you will learn while you're here at the university to approach and solve problems that you've never seen before, right? That's the real key. While you're here, we're able to tell you a little bit about engineering. And hopefully that's going to be your start for a career in this. So some people see the fact that technology is changing all the time as a bit of a burden. I don't. I see it as a huge opportunity, mainly because I like learning things. Okay? That's why being an academic here at the university is like the perfect job to me, because I'm always having to learn new things. And I'm hopeful that, you know, what I have sort of learned painfully and slowly, because I'm a bit of a thickie, painfully and slowly over the last 30 years, I can distill down into something that's easily absorbed by the students, right? That's our role here. The university is very hot on what we call research-informed teaching, which is people who are practitioners in the field, right, get to distill their knowledge in concentrated form for the students. Anybody who gets into engineering school, you know, is clearly very bright by all sorts of measures, and you could learn everything from a textbook, right? But engineering is very much about doing, right? It's a very creative process. But let's get back to electrical engineering. Everything these days about electrical engineering is pervasive. You find electronics everywhere, from the humble dishwasher to the smartphones that we've talked about, to cars. Modern cars, right? We tend to think of cars as mechanical things. Well, there wouldn't have been the advances in fuel efficiency, safety, and all those other good things without electronics, without electrical engineering. There's something like 60-odd microprocessors in a modern car controlling everything from the engine management system to how quickly the windscreen washers, wipers operate. Okay, so the technology is everywhere. Sometimes people say, well, you know, are there jobs available? Like isn't everything being automated? Yes, but who's doing the automating? Right? It's the electrical engineers. With everything becoming embedded with electronics, there will only be an increasing demand for electrical engineers, not a reducing demand. We do a lot of cutting-edge research here. Wireless charging of electric vehicles. Right? This is a technology that this department, in fact, is quite famous for. We've licensed that technology to various companies around the world. This slightly stylistic diagram here is showing how the car, as it's driving down the street, is being charged from small coils placed in the ground. And it's actually able to transmit tens of kilowatts of power from the road, embedded in the road, into the vehicle as it's driving along. I can tell you now that roughly half of you are using technology that was invented in this department and licensed to outside companies for some crazy reasons. We're not allowed to reveal what that technology is or who bought it, but yeah, you're using technology every day in equipment that you have bought from overseas manufacturers that contains intellectual property and electrical engineering technology developed in this very department. Lots of things are on the horizon. They're quite exciting. An obvious one is self-driving cars. There's been a lot of hype about self-driving cars over the years. When I was a little boy, the future to me was flying cars and robots. I've been let down on both of those fronts. But, you know, we're getting closer. Certainly the problem of self-driving cars is enormously complicated, and it's not just one of electrical engineering. It requires machine vision, machine learning, artificial intelligence, radar, LiDAR systems, all sorts of things. And it's proving to be a real difficult problem to solve. But now people are talking about perhaps not being fully automated, maybe they'll be partially automated, and we're already seeing some of that today. If anybody owns a Tesla, there's all sorts of cool features in those cars that assist you in some way. You still have to hold on to the steering wheel, though we're not at that point yet. The big thing that's coming, the Internet of Things, all the brouhaha you've heard about in the press over 5G. Let me just tell you now, 5G does not give you cancer, all right? What 5G will allow us to do is to have connected devices. See, the internet at the moment is very good, connecting one person to another or a person to a machine. And soon we'll be able to have machines, well, we can do now, but this will just cause an explosion in the ability of machines talking to machines. Machines telling us, reminding us to do things. Our cell phones already do that sort of thing, don't they? They remind, I couldn't live without my cell phone reminding me what I have to do every hour of the day. Now, in the early days of the Internet of Things, people came up with ridiculous things like, well, the fridge will be able to tell you when you need more milk. I've solved that problem already. I just open the fridge door and look in there, and I can tell straight away whether I need more milk. I don't need the fridge to text me, you know, when I'm out to dinner, reminding me to bring more milk home. But there are lots of real applications now, when suddenly people are starting to see there's a way to make money, there's a way to automate things, there's a way to make businesses run more smoothly if we can have devices talking to other devices and things happening automatically. To an electrical engineer, this is a lot of fun. A lot of us are drawn into this because we like solving problems. We like coming up with solutions to other people's problems. This seems like a no-brainer for the sort of thing we would like to get into in a big way. Sometimes things have downsides. Things like Facebook, stay in touch with the extended family. Twitter, just get news out there very quickly, even from, you know, places that are having trouble with their democracies and what have you. These all sound like very noble things, and this is often why we as engineers are drawn into developing those sorts of systems. And then it's only over time that problems emerge. Who could have foreseen the sort of terrible bullying that goes on online now, you know, with a system that was ostensibly to keep people connected, to sort of maintain that social bond that's sort of kind of difficult to maintain in a modern society. Similarly, with this sort of thing, with the Internet of Things, wouldn't it be great if you could have a little tag that you put on your child when they go off to school in the morning so that you can know where they are any minute of the day? Sounds like a great safety feature, certainly keep everybody's stress levels down, but it only takes a few seconds of reflection to think, that's a really great thing, but it could also be a really bad thing, right? And as engineers, this is a dimension that we have to grapple with, and this sort of thing is also covered in the degree. There are ethical issues. It's important that we try and imagine what's the downside of what I'm doing. What could possibly go wrong if I solve problem A? Am I actually creating another problem B? Smart cities, the list goes on. So we've got the Internet of Things, we've got the automated driving systems. Soon, in order to pack more and more people into less and less space, we're going to have ways of simplifying the operation of large groups of people, which is usually cities. There's a never-ending need for electrical engineers to help solve these problems. Further into the future, we've got cool things like this. This is called ultra-dense memory. It's 1 million times more compact than a CD. Now, some of you are probably saying, what's a CD? Well, when I put this slide together the first time, CDs were a thing. So about 10 years ago, I first used this slide somewhere, and I said, this is in the future. Unfortunately, it's still in the future. So I don't want to paint a fully rosy picture that every great idea that we come up with turns into an awesome, labor-saving product, but it is kind of awesome. There are 40,000 billion bits per square centimetre. That's just fantastic. This is the surface of ultra-dense memory, and each one of these dots is one atom, and the presence or absence of an atom represents a binary 1 or a 0. So you literally can't get any more dense than this. It's got a similar information density to DNA. And why isn't it here? Well, you can have bright ideas, and you can even get them to work in the laboratory when they're connected to $1 million worth of test equipment. But it's another thing altogether to mass produce them, to get them out into the market. And so there are all of these extra issues that electrical engineers need to know about, right? But that you will learn when you're here. Okay, so what about the department? So the department is the Department of Electrical, Computer and Software Engineering. We offer 3 specializations. You may have even been to some of the other talks on computer systems engineering and software engineering. Electrical and electronic engineering is our oldest and broadest specialization, okay, which covers the most. If your only burning desire is to learn about digital hardware systems and the associated software, then you might want to do computer systems engineering. If your true love is software engineering and writing the ultimate mobile app or database system or whatever, then you might be interested in software engineering. If you'd rather have a slightly broader exposure to electrical engineering, then the triple E degree, as we call it, is probably your thing. So as engineers, what do we like to do? Well, we like to solve problems. You probably like to solve problems. It feels terribly good. It's very rewarding when someone at school, for example, comes to you with a problem and asks for your help. You're able to solve that problem. Maybe it's a calculus problem. Maybe it's some other sort of problem. Inherently, we like to solve problems. It makes you feel good. There's a little little kick to your self-esteem, right? But you get to do that all day, every day. And although it sounds rather high-minded, basically we want to apply scientific knowledge to human needs. Remember that it's the scientists who study nature, find out about the new phenomena, and engineers are always saying, right, how do I take that science and solve a problem with it? How can I bend it, adapt it, use it to solve some problem? And as I mentioned before, because it's important, we spend a lifetime of learning. Right. To me, that's a good thing, and I'd like to think that you will think it is as well. Now, when we look inside our department, we see this rough categorization of the sorts of things that you've learned. So you learn about computer systems, and I don't mean PCs, I mean the computers that are in just about every piece of equipment these days. Control systems, right, how do we keep a drone flying level, that sort of thing. Robotic systems, how do we have a robot arm gripper pick things up? How does a robot navigate a hallway full of people? That sort of thing. Electronic systems, power systems. How do we make a better power network? Photovoltaics, wind power, hydroelectricity, that sort of thing. Radio systems. How do we get a radio signal from inside here, across the planet to somebody in the northern hemisphere? Signal processing. How do we efficiently get signals back from Mars when we've only got very poor quality, what we describe as channels, a communication medium, right? Software engineering. How do we make it all happen, basically, control it? That sort of. So these are the things that you would study. These are in broad categories. You may choose to do subjects in some of these areas and not others, depending on your tastes and interests. So we don't make you do everything. There are electives where you can choose what you want to do. So if you're interested in cybernetics, you might do computer systems and robotic systems and software engineering. Those 3 things naturally go together, to do things like that. If you're interested in wireless charging of vehicles, maybe you do electronic systems and power systems. This is being reversed. I don't know how that happened, but Sometimes technology is hard. If you like drones, right? Drones need control systems for the flight controls. They need electronic systems to power motors and all the other electronics that are on there. You'd actually need radio systems as well if you want to beam images back from the onboard camera, all of that sort of thing. These are all things that you can do, and you get to choose what you would like to do. Exoskeleton man here, he's wearing an exoskeleton, a skeleton on the outside of his body to help him walk. You probably need just about everything there in order to do something like that. As the technology applications become more and more sophisticated, you need to draw in more and more disciplines, and frequently we have to work with other departments as well. So it's very common for us in electrical engineering to need to work with mechatronics, mechanical engineering, chemical engineering in order to do certain types of projects. All right. Now, if I haven't yet convinced you that electrical and electronic engineering is an amazing thing to study, one thing you could do is come along to our Part 4 Project Open Day. The final year students get to work on for the entire year, they work on a fairly large project, the biggest project they work on before they go out into the real world and get a job. They work in pairs, and on Friday the 11th of October in the afternoon from 11 to 4, all of those projects will be on display. So you can go along, you can speak to those students, ask them how they have found the degree, what did they like about it, would they do it again if they could do it all over. Get it straight from the horse's mouth. And I think you will be amazed because they work very hard. They come up with amazing creations because, as I said earlier, engineering is a very creative process, and that's one of the ways it's very satisfying. Look, that's all I wanted to say, so I'm very happy to take some questions, and if we run out of time for questions, I'll lurk about outside for a few minutes if you want to talk to me out there. So anything immediate, or it's been a long day, so maybe you just want to get home. I understand. No? All right, then, oh, hold on, one question here.
What do you have to take to get in?
Very approximately physics and maths, but the people at the front door will be able to tell you precisely what you need to study. Yeah.
For engineering, you just need calc and physics, but that is level 3 calc and physics, and a rank score of 260. It hasn't changed from what it was for my year, but those are the only 2 important things you need to take.
There you go. Couldn't be simpler. Any other questions? All right, look, thanks very much for coming. I appreciate it.